In this video, we're going to look at conditional probability. And conditional probability is where we have been given a little bit of information about the type of outcome that we get. So the information that we get helps us to reduce the sample size that we're working with. So, for example, have a look at the people in this picture here. And I want to work out the probability that a person within this group of people has green eyes, and the person that I'm choosing already, I can tell you, has red hair. So immediately your eye is drawn to just the people with red hair in the picture, and you disregard everybody else. And that's what happens with conditional probability. Given that the person has red hair, immediately you just disregard everybody else. What is the probability that they have green eyes? So the numbers that I've got here in this Venn diagram don't actually fit the number of people here. But say I had 20 people and 7 of them have red hair, 5 of them have green eyes, and there's 20 people altogether. Given that the person has red hair, so now I'm just looking at these people just here, what is the probability that someone has green eyes? So these are the people that have green eyes as well as red hair. So the probability that they have green eyes, given that they have red hair, is 2 out of a total of 7. That's our probability. And you can see now that our people with red hair, this circle here, is now our sample space that we're working with. So normally the way that it's written is in this form of statement here. What is the probability of something occurring given that something else has already occurred? That's the normal way that they would write it. And we set it up so whatever the probability is up here is our event A. So let me put here an A, given that B has happened. And what we had before with our red hair was what is the probability that they have green eyes, given that they have red hair. What you have, the numbers that we used were the intersection of the red and the green, so the intersection of the two things that you're trying to find, divided by the probability of our new sample space. Now this will work as long as the probability of B is not 0. And I want you to notice something really important here, that this is not the probability of A. Okay? That's a mistake that people make in the exam. They write it as if it was just probability of A over probability of B. In some cases it is, but generally that is not what conditional probability is. Okay, so make sure in the exam that you are getting the formula correct and you're checking what the intersection of the two events actually is. Okay, so in the question it says, what is the probability that a person has green eyes given that they have red hair? So the given that they have goes in the second bit of the statement, and it also goes on the bottom of the fraction for probabilities. The probability that you're trying to find, which is the probability that the person has green eyes, is the thing that goes in the front, and the top is the intersection of the two. And as we said before, it's 2 out of 7. Now you will have worked already with conditional probability on dependent tree diagrams, where what happens in your second choice, the probability of it is different depending on what happened in your first choice. And we can show that this is true if we start with our conditional probability formula and we rearrange it so that we get the probability of the intersection. So the probability of A and B occurring, so intersection means and, so A and B occurring, what you actually get is the probability of the first branch B. So this will be probability of B. And this particular value here is the probability of A given that B has happened. And so to find the probability for that particular branch, you take probability of B, which is this thing here, and you multiply it by the probability of A given B. Let's look at an example. See if we can get this to fit. Okay, so let B equal the event that it rains on Friday. So this is rain or not rain on Friday, and A be rain on Saturday. So this is Saturday's choice of what happens. Okay, let me move this down a little bit. So we have here that the probability that it rains on Friday is 0.3. So let me put that onto the tree diagram. Raining on Friday is B, so that will be 0.3, which means the other branch is 0.7, because any split on the tree has to add to 1. If it rains on Friday, so that puts us on this branch here, if it rains on Friday, the probability it also rains on Saturday is 0.4. So this branch here has to be 0.4. And this statement here can be written if it rains on Friday, so given that it rained on Friday, what is the probability that it rains on Saturday? So that's our conditional probability there. So the top branch of that split is 0.4. There's only one other possible option here, which means that this branch must add to 1 with this branch, which means that this is 0.6. And that is the probability of not rain on Saturday, given that it rained on Friday. And so you can see that there's lots of conditional probability statements. Every single one of these calculations or these numbers here is actually a conditional probability. So let's just fill in the last bit. It says if it does not rain on Friday, so which is this one here, the probability that it also does not rain on Saturday is 0.7. So let's write that as a conditional statement. So the probability that it does not rain on Friday. So we know that it doesn't rain on Friday, so that's B dashed. What's the probability that it doesn't rain on Saturday, which is A dashed, is 0.7. So I'm going to put that on down here, 0.7, which means this other branch is 0.3. So again, we've got conditional probabilities sitting here on our tree diagram. And the other one obviously sits in here. So what about conditional probability and our tree diagrams where we have independent events? We know that this branch here is a conditional branch. Depending on what happens to be, A will have a different value. So let's just pretend that that is in fact the case, that what happens here depends on what happens here. So our probability for B intersect A is actually equal to the probability of B, which is this one, multiplied by the probability of A intersect B. So we have this formula down here, from our tree diagram. We know for independent events that the intersection between two independent events, the probability of the intersection, is equal to the probability of A times by the probability of B. And so we actually have the same statement here. We have two different definitions for the probability of A intersect B. So what would happen if we put the two together? So if we put the two together, I'm going to take, this side from the top one, which goes there. And I'm going to take this side from the bottom one and put it there. So they are both actually the same amount. If I then divide both sides by the probability of B, as long as the probability of B isn't equal to 0, I get this statement here. So for independent events, we have a new formula that we can use to check whether independent events are independent or not. Now this isn't on your formula sheet, so this is something that you need to put into your bound book of notes. So this is just the same formula rearranged, and so you should have in your bound book of notes for independent events, you should have two statements. And if we just stop moving it around, if we just take our first statement that you should already have in your book about independent events, and we replace the A intersect B in this equation here for our conditional with what we had up above, you can see that the probabilities of B's cancel, and we do get the formula that we had further up, that if the events are independent, you'll get the probability of A intersect B given B is equal to the probability of A for independent events. That's just another way of going through and showing you that it is in fact correct. That's the relationship. So I want to do one example of this before we round up this video, and then I'll do another video that goes through the VCAR basic probability questions where they use lots of combinations of mutually exclusive events and independent events, conditional events, and get you to try and work out probabilities based around those. So this question gives us probability of A is 0.6, probability of B is 0.3, and the probability of B given A is 0.1. So they want you to find probability of A intersect B. So you need to think about all of the different formulas that you've got. So we know for probability of A intersect B that that's part of this conditional formula. So let's start with that and substitute in our known values. We have that probability of B given A is 0.1, and that we're asked to find A intersect B, and that the probability of A is 0.6, not 0.6. And so now just multiplying both sides by 0.6, you'll get 0.06. And can I just say really, really carefully here, this is another mistake that people make in the exams, okay? Beware of your decimal multiplications. Okay? Just be really careful with them. Make sure you're getting your decimal places in the right spot. And finally, we're asked to find the probability of A given B, which is this one. And we actually need to use the formula for it. It's not the inverse. So make sure that you write it out and substitute in the values that you just found. So A intersect B over the probability of B, which we have up above in our question. So we just found that the probability of A intersect B was 0.06. Our probability of B is 0.3. So we're going to do that particular division. And if necessary, make them have the same number of decimal places so that you can see that it is really 6 divided by 30. Which is 1 on 5.